Good morning. Well, it does work. The microphone has come on. I guess you can hear me at the back. You probably hear me in the chapel, actually, from this volume that I can hear for myself bouncing off the back of the auditorium. My name's Brian Cartwright, and I'm Ofsted's National Lead for Science. So if you do have a question, please do not identify the school you come from, in case my friends come round to check. This is about science inquiry and what we find makes for the best practice of science in schools. If you've had a chance to look at maintaining curiosity, it's about, I suppose it was published best part of 2 years ago now, but nothing much has changed in terms of our ongoing experience of what is going on in school science teaching. And it does, its title really, points out what we feel is the duty of a science teacher, first and foremost, is to maintain curiosity. You know how doctors, first and foremost, swear, actually, to uphold that Hippocratic oath, first, do no harm? Science teachers, first maintain curiosity. And if that's in your heart and in your mind, if you're thinking as a teacher and a manager of science in schools, you'll be fine. Problem is, it's not necessarily there in everybody's hearts or minds, and the further up the leadership of a school system you go, in some cases, the further away thinking goes from maintaining curiosity, and the closer it gets to getting good grades in GCSEs. And some schools find that a conflict. They are wrong. The best way to get great grades is to maintain curiosity. But nevertheless, there can be a distance between that thinking in some schools. So your first mission today, early in the morning pretty much, it is a Friday I suppose, but at least it's Friday morning. Here's a question, why teach science? Now, what I want you to do, now you have 2 minutes, and I haven't got one of those little do-do-do-do-do-do type of countdown thingies that you'll sometimes see in schools, but 2 minutes to read, learn and immediately digest this paragraph. There will be a short test afterwards. Perhaps I won't give you 2 minutes, actually. Now then, do not share who you are, but anybody want to disagree with that? Any dissenting voices out there? Why teach science? Pretty much happy with that? You're a dissenting voice, that's fine. There's a bit of a pit. Oh dear, what's happened there then? Ah. It's the law. This is the national curriculum for science, and it's why the government feels science should be taught. And one of the things, it's not just that knowledge stuff, it's the bit about recognise the power of rational explanation, develop a sense of excitement and curiosity about natural phenomena. That's the law. You are expected in schools to be developing those attitudes, not just ticking off the content box stuff. Is this not working?
It's connecting, trying to connect. You were going to, let me just put that off so it doesn't do that. Sorry. Right, we should be fine now.
Sorry. Whilst Chris is dealing with the technology, the national curriculum, by the way, you don't have to teach it if you're an academy. You work that out technically. But if you look in academy agreements, you will find, I can't remember which, paragraph 22 or 26 or something, there's very explicit requirements for academies to teach English, maths and science. And it then sets out very explicitly the evidence-based base of science. It's there in part to counter some attempts to deny some aspects of science evidence, for instance evolution, and that's why the academy specifications do include science and its link to evidence-based understanding. Science in schools is probably the subject where that science or evidence-based approach is required. And you as science teachers and leaders are, in that sense, the sort of holders of that duty to connect evidence with understanding and that notion of curiosity and finding out. Many teachers haven't read this paragraph. When you get a new national curriculum or a new syllabus or whatever it might be, the temptation is to jump to page 72 to see how you teach, I don't know, acids and bases differently this time round compared to the last time. The devil is not in the detail. It's this opening why teach science that we want to make sure teachers recognise is what is the best practice. And we will be looking for that as Ofsted inspectors, of course, just checking that the experience kids get is actually developing that curiosity as well as making sure they understand some of the big ideas. Right. It's the law. In maintaining curiosity, we found 3 things common to all good science outcomes for pupils. All 3 have to be here before those outcomes are good or better. And the first thing is that the subject leaders actually put scientific inquiry at the heart of science teaching. So they know to make sure that there's resources, time and professional development for their staff to make sure those teachers are giving kids opportunities to find things out, to do experiments, to read other people's experimental evidence, to ask questions, to raise questions, to experiment, to try, and if they need to, try again, and to modify the experiment. All of that inquiry-based learning, trying, not getting it right first time if the right is the right word to use, improving the experiment, making it more reliable, that is what good science teaching is about. And it's connected to how children learn science. So your science leaders should have training in how children learn science, which is through doing it, of course. But there are schools where subject leaders are sometimes not scientists, particularly so in primary schools. Sometimes in secondary schools, subject leaders may well have a science background, but have not had any science leadership training. They've had generic middle leadership training, so they know how to do lesson observations and fill little checklists in and that sort of stuff. But do they understand how kids learn science? Do they maintain and improve their understanding of that? No. Second thing, although they sustain that national curiosity, pupils become interested to learn the subject content. The actual subject itself should be interesting. And it's not difficult. All of us as teachers have ultimately, you need to rely on the science. The things that wriggle, bang, pop, squeak, whatever it might be, the actual phenomena itself needs to be in lessons. Sometimes you can't physically do it inside the lesson because it's too dangerous or too big or too slow or too fast, so you can use ICT and video and all sorts of ways to bring the ideas to that classroom. Very often you can do the science in the classroom, but we sometimes see this kind of model. If this is you, I'm very sorry. I don't think it is, hopefully, because it wasn't a school around here that I was watching this done. But this was, I don't know, a year 8 lesson on leaf structure. So can you imagine the diagram? There's a big diagram of a leaf with cuticles and waxy layers and guard cells and stomata and all sorts of stuff on the diagram. And around this room were six stations, and each station had like a textbook or a piece of writing about the particular bit of the plant. And the children took a worksheet, which had the diagram on, with empty boxes in it at the moment, to each of those stations and copied the information from the station into the box. So at the end of the lesson, each child had the worksheet with the, I'm assuming they copied it accurately, correct information about a bit of a leaf. Was there a leaf in the lesson? No. No actual leaf was harmed or cut or looked at in the developing of that knowledge. Now, could the kids answer an exam question on what's that thing about a leaf then? Probably yes, they could if they remembered it. But that isn't teaching science, that's teaching kind of a general knowledge quiz type of thing. Like kind of a mastermind approach to teaching, as opposed to an understanding what a leaf is about. Similar example, and this was near Rolls-Royce in Derby, where they make jet engines. And probably at Rolls-Royce must be one of the biggest suppliers in this country of titanium. Fantastic metal if you've ever come across it. It is light and strong. It was another sort of lesson. You potted around to different places in the class and copied stuff about titanium and aluminium and copper and iron, and at the end of the day had a list of properties of those different sorts of metals. Aluminium is light and strong. Steel is strong, whatever. but no actual metal in the room. It's not difficult to have rods of each of those kinds of metal and just feel them. And if you've ever done that and felt a piece of titanium compared to a piece of aluminium is light, but it's not strong, relatively speaking, compared to titanium. It's awesome stuff. And that would have just shifted that lesson into that's what it's really like. That's what these metals feel like, at least. And it's quite easy to do as a science teacher, to just put the phenomena into the lesson as well as the fact, if you see what I mean. Third thing, accurate and timely assessment. So how well are those youngsters developing their understanding of science concepts and using their skills in analysing and interpreting the experiments that they're doing so that your teaching responds to what pupils understand? Now then, to get to understanding, essentially children have to tell you what they understand about a big idea. It's not what's the name of this bit of a leaf. That's not understanding. It's what does this bit of a leaf do? Why does it have to do that? What would happen if it wasn't doing it? Can you understand how a leaf is working and how all of the bits hang together in that leaf structure? Now, generally speaking, children can't do that. They can remember the labels, but they can't explain what the things are for. To get that understanding, or for you as a teacher to get that understanding, you do need kids to talk to you in more than single words, or to respond to your questions in more than gaps in missing word things or multiple choice things. It's quick and easy to check their knowledge and recall doing that, but it's not very good at checking their understanding. They need to talk and write at length so you can pick up their understandings and misconceptions. And in this internet age, you do have to check that if you give them extended things to go and find out about, they're not copying and pasting from Wikipedia, of course. So you actually make sure it's gone through a child's brain first before you assess what they're actually responding to. A great example of that was a young new teacher, actually, somewhere in the southwest. She'd set her homework about sort of the expansion of the universe, I think. So at the end of the day, the youngsters had done some homework on the expansion of the universe, and there was all this stuff coming in about redshift and how that's quite, but it is actually a marvellous bit of science and an awesome bit of, gosh, it must have started type of realisation, you know, a few decades ago when the penny dropped that the thing's all moving apart, which means it must have vaguely started off from the same place. Anyway, so the teacher had underlined what's redshift, because she didn't believe the kids were actually knowing what redshift was. They just copied this phrase, redshift, into this is how we know and actually the kids would then read, well, redshift is, and it's light and all that Doppler effect and the rest of it. So that, you need to check they really do actually has gone through their head before you actually assume they do understand what's going on. But it's great fun to do it. Okay, we found in the best schools, pupils understood the big ideas of science. The ASC, Chris has just mentioned those, that sort of work that they did a few years ago now in terms of cataloguing a set of big ideas. There's no limit to how many ideas you can, but they catalogue these in a way that's quite straightforward for science teachers to get a grasp of. And in those circumstances, they kind of connected the detail of an experiment with a bigger idea. And that means as a science teacher, you know where this is going. You could look at curriculums to do that for you, assuming the curriculum has been constructed in the systematic way, which is a bit of an assumption, but let's pretend there is an element of progression. There is in the big picture side of things. But either way, as a science teacher, you need to know why it is you're teaching this bit about, I don't know, filtering muddy water, whatever it might be, because that connects with the particle model, ultimately, little bits and smaller bits and so forth. So down the end of that filtering muddy water experiment is the connection with the particle theory of matter. And it's those connections that science teachers should be aware, such that they can answer what we're doing this for questions to the people. Why are we doing this then? It's because it will give you a bigger idea of where we're going with the concept of, in this case, the particle model. So be comfortable with knowing that and be prepared to share that with the children. It's best if they could understand the importance of the ideas for themselves, rather than you tell them. But occasionally you can tell them. We call this in Ofsted speak imparting knowledge authoritatively. I don't know, but lecturing, for example. And just occasionally, just tell them. You are the expert. And it is fascinating to listen to an expert explain. There is a thrill and privilege of that. And many of you will have experienced that from experts sharing with you their understanding of a difficult idea, and they've broken it down into small enough steps for you to kind of get it now. And that's an important part of teaching. So that's fine. I mean, I saw that, you know, so Ofsted, by the way, we don't mind if you sort of lecture the kids, as long as it's a good lecture, and the kids are actually learning from it, and you can tell from the attitudes and the questions they throw back whether it's actually going in and engaging their interest. Now, this is old data now because it'll be substituted by what's happening in science, GCSE stuff. The goalposts keep moving from one year to the next, and it's very difficult to make year-on-year comparisons. I would just throw in with this, though, this notion of girls not continuing to study physics or related engineering studies post-16. And this is not unique to Britain or England. But we think it's most likely connected to not seeing what the physics is for at an earlier stage than Key Stage 4. Key Stage 4 is too late for most youngsters to be making them or changing their minds. So the kind of directions of travels are being set at Key Stage 3 and late primary school. And the more we look into this, and not just Ofsted, lots of research is trying to get to the bottom of whether schools can behave differently to produce a different behaviour in terms of choices post-16 for girls. It's potty that, I don't know, something like 40,000 boys and girls-ish study biology post-16. It's about the same for chemistry. There's slightly more girls than boys doing biology, sort of like 50,000 girls, 40,000 boys or something. I'm ballpark numbers here. Chemistry, it's about 35,000 of each are doing chemistry post-16, but in physics, you've got about 35,000 boys and around about 8,000 girls. It's just the physics that they don't do. It's not the chemistry and biology, and actually, there's more girls than boys doing science post-16. So it's not science they don't want to carry on to do, it's physics. And that huge talent pool is being lost to the physics and engineering and those disciplines and skills. And clearly there's potential damage to the economy because of the importance of those skills in making things. Part of that comes down to teachers themselves not having a clue what you can use physics for post-16 and 18, actually, or parents. And in this particular, I'm a parent as well as an Ofsted inspector. I'm married to a physics teacher, so I suppose we're a bit biased, aren't we? But I don't know really what you can do in physics. I know what I did, and I know what my wife did, but I don't really know the range of careers available in physics. But if you ask me about biology, though I'm not a biologist, I can come up with quite a long list, mainly medical connected, or environmental science connected, or whatever. It's that background, anecdote capital, I think it's sometimes called, isn't it, in terms of what conversations youngsters are having with parents, with peers, with teachers about their futures. Engineering won't crop up very often in that conversation. It's a word that's missing pre-16 pretty much in most schools. And the D&T agenda, bless it, he says carefully here, doesn't get close to engineering very often, and in many schools it's drawing pictures first before making the sort of thing afterwards. So they will design a pizza on a piece of paper. Okay, but at the end of the day, it's the pizza you actually want to make and test it and see whether people really like it or not, rather than whether they like the drawing of it. Anyway, I could get a bit cross by that. Leaders in schools, not necessarily monitoring what's going on. They don't know where the pupils go post-16. And by the way, if you are in a school and you are a leader, we will be asking during school inspections your sort of progression information. Where do they go next? What do they study next? Have you analysed in any shape or form profiles, groupings of where youngsters are making choices, and are you doing anything about stuff that sticks out of line? We just published earlier this year a table showing the proportions of youngsters studying different post-16 subjects. And in that, you can see the physics sticking out like a sore thumb. By the way, while we're on the physics banging on, the take-up it's probably gone away now, but AS to A2 for girls is really awful for physics as well. So even though 8,000 of them do AS, another sort of third of them drop out when it comes to going to A2. It's the highest dropout of any AS subject. Right. There you go. Get children involved in planning, carry out and evaluating investigations. That's where science achievement is highest. You know, those of you that have been doing this project research, it does improve achievement. Because it improves, but they're better at doing science ultimately. It's quite important that kids have a say in what they're doing as well. So they've raised questions, or at least contributed to the inquiry that's taking place. Teachers need to structure that quite carefully, so we don't want them to see if they can sort of bump into the structure of the atom spontaneously. You will need to guide their directions of inquiry, but they do need to raise questions. Let's give you an example about how a straightforward experiment can be twisted from a recipe to an inquiry. I'm a chemist, and you know that experiment where you add silver nitrate to the chloride, bromide and iodide salts, and if I'm remembering correctly, chlorides go white, bromides go creamy yellow, and whatever it is, and it goes yellow, yeah? So I saw in the school that experiment being done, the test tubes are out, the children followed the recipe, step one, get your test tubes from the front bench, wear your goggles and all that. Eventually they added the silver nitrate systematically to the tubes, recorded in the pre-prepared table, so all they actually had to do was follow the recipe, drop the nitrate into the halides, record the colour. So at the end of the day they had the correct answers in their table. Same school but a different teacher had the same equipment, but he said, find out which one of these 4 tubes, all containing a clear solution, which one is which. Off you go. And at first sight, how do you do that? I don't know which one is which. No, you don't. That's the point. You need to find out how you do it. And at the end of the day, you have to pair stuff up and try A with B and B with C and C with D, etc., etc., etc. And eventually they'll work out one of them always causes a colour change, so that must be the nitrate and so forth. So for the same materials, but with a completely different approach, the kids, instead of following the recipe and talking about what was going on in the playground, actually had to think about how they were going to do this. And it's often as simple as that, changing the climate. Primary lesson, same sort of thing. Teacher gave out plastic mirrors and homemade ray boxes using torches and a bit of insulation tape, and said there's a rule about how light bounces off mirrors, find out what it is. Opposite end of the spectrum, similar approach, although to be fair it was refraction rather than reflection. Year 11 top set, most able children in the school. Teacher said, okay, I'm giving you a worksheet. These are top set children, by the way, well capable of actually writing for themselves. They don't really need scaffolded worksheets, but never mind. They were given a worksheet. On this worksheet was a rectangle already drawn, which happened to be the same size as the glass block they were about to be given. And actually what these bright kids had to do was to put the worksheet down, put the glass block over the outline, line the ray up down the already drawn incident ray on the worksheet, and just copy where it came out on the far side. And then measure some angles, and they would have then learnt the laws of refraction. Well, okay, you could have done exactly the same thing with top set key series 4. There's a rule about how light bends through when it goes through glass. Find out what it is. It would have taken a bit longer. You might have to have suggested, why don't you take the signs of the angles? Because I don't suppose I'd have thought of that off by heart. But that's a completely different approach, and they would have then discovered refraction and Snell's law and maybe internalised it in a way that just copying the recipe wouldn't have done. Primary schools, differentiation, most able, we call them now rather than more able, to build on our prior learning. This is quite important as well. I think schools are now thick with information about prior learning, well, at least prior scores in previous tests. That's not necessarily the same thing. And we often see lesson A, especially in secondary schools, less of a problem in primary, but I'll come back to a primary problem in a minute. Lesson A is where there's a class list, so I know as an inspector I can see these different starting points in terms of their Key Stage 2 data or whatever it might be. I can see that 1 or 2 have got pupil premium flags set, or some has got special needs flags set, or EAL, or whatever particular grouping they're in, so stacks of information. Then I can see a lesson plan, not that we want to see a lesson plan, but just pretend I've been given one, which has got different tasks, some, most, or almost some, that way around. And off they go, and sure enough, all of them do all of it, some of them do a bit more, and a few do an even bit more still. So let's call that lesson A, shall we? I've never seen a lesson B. I have never gone to a lesson that's carried on from those different ending points that was planned to happen in lesson A. It's just another lesson A. So teachers aren't thinking about the consequences of even that relatively crude differentiation by outcome model. They're just carrying on from a fresh start all the time. If teachers were thinking on their feet, they'd think, right, those lot got that far yesterday. I need these lot to go further. Those clearly need some more consolidation because I haven't fully understood the main idea I was looking for. The thing kids start doing different things, well, yeah, they do. That's the consequence of actually looking at differentiation seriously and building on what kids have already done and already understand. But it's rare to see it in secondary schools. Now, in primary schools, you see it all the time in English and maths. But those same teachers don't do it in science lessons, funnily enough, even though they know. And they're really good at it, at doing it in the maths and English lessons that happen before lunch, generally speaking, by the way, for some potty reason. I don't know why you can't do science before lunch, but there you go. But come to a science lesson, bang, it's all one size fits all, almost some. At worst, you've got more able kids attempting to teach less able ones. No, don't do that. You need teachers to teach those that are struggling to understand stuff. It's hard to work out why kids don't understand stuff. Professional teachers find it really difficult. So getting you more able to teach a less able, that isn't challenging your most able. Now, I understand it's helpful to be able to explain something to somebody because that reinforces your own ideas. Of course it does occasionally. But no, you want your least able children taught by the best teachers you've got, which hopefully is the classroom practitioner. More able ones can be researching stuff themselves, checking as they go, giving them more demanding versions of the same initial task. Right. Teachers' feedback to pupils on how they might improve their work is a common area for improvement. And Ofsted got a bit told off recently about implying particular marking styles or frequencies. No, we don't. We just, if you're going to assess kids' work, make sure it's worthwhile doing so that it really is testing their understanding, and then from that, interpret how they understand an idea and make suggestions as to how they might improve it. Don't want to dwell on that particularly. Literacy is really critical. Imaginative science contexts help pupils make good progress in both subjects. So, homework for the Harbour principle, you know the Harbour process, sort of making ammonia, I think it is, and you can't really do that in the lab. So it is a phenomenon you have to talk about rather than demonstrate, I think, physically. Homework for that project in preparation, find out why Fritz Haber's second wife left him. What's that got to do with the Harbour process? Well, it's got a huge amount to do with the consequences of Haber's work. And the kind of connection between, well, it's science and society stuff ultimately. And this particular process helped the First World War last 2 years longer than it would have otherwise done, because the Germans were able to synthesise explosives rather than get nitrates from Argentina. And it's also fed the world. Same chemistry, different application. And all of that stuff thrown into the Harbour process really contextualises H plus N equals NH3 and all equal. That's really critical to maintain curiosity in the young people, even if it's a theoretically based lesson. Tracking in primary was a particular problem. There we go, the last point here. Where teachers get subject-specific training, outcomes in science are almost invariably good or outstanding. It's not rocket science, this. If you learn how to do the job better, you're better at doing the job. Now, you're here, so it's already indicative that the schools that have let you come want you to get better at your job, and that's likely to make that happen, so there's a kind of positive reinforcement culture going on. I found a school last week, actually, that every teacher was involved in an action research project. 1 period a week on their timetable is allocated to action research. That's a huge investment from the school's point of view. You know, about 4% of their teaching budget in effect. Fantastic, though. Is that school flying? Absolutely. Because the teachers are valued and trained, and they're doing a really good job. Right. I'm going to whiz on a little bit here because it's not particularly critical for scientific inquiry, but this bottom one, time to work independently, time to develop the practical skills is sometimes missing or clipped. The clue to this from an inspector's point of view is when we do a work scrutiny, either in primary or secondary, that phrase, finish this off, appears fairly regularly in those little results tables. There's 2 or 3 numbers in and there should have been 20. And you'll see, finish this off, question mark, or whatever it might be, or even question mark, which is the simplest form of feedback I've ever seen from the teacher. But it does mean you haven't finished this yet, actually. But if we see that repeated, nobody's taking a blind bit of notice of the marking and feedback. Whatever the task is being set is not being considered important enough to finish by anybody. And it is important you finish an investigation. You might not get the result you were expecting. That's partly why you're doing the experiment, to find out what is going to happen. But it is important you get to the end of the journey. It is important also to develop practical skills. You wouldn't expect a driving test to take place with just one example of a lesson beforehand. You need to practice how to handle the kit, choose the right apparatus, and manage experimental methods in terms of the kind of, the rules, for want of a better phrase, of fair tests and reliability and whatnot. Then that doesn't come naturally. It needs practice. It also needs practice getting it wrong. So it's much better for kids to design an experiment that will end up going wrong because they didn't isolate variables and then learn from that than it is to structure it for them into a recipe where they don't have to actually think at all about the different sorts of variables. Great example where that worked really well was a sixth form lesson on gravity that I saw, where the students were dropping things or oscillating springs or making pendulums. There's all sorts of different ways to measure G. 9.81 for those of us that can remember it all those years ago. And 6 different groups came up with 6 different answers for what was supposed to be 9.81 because they'd done 6 different experimental methods. And until the teacher said, okay, who's right then? Who's got the best answer? Those students haven't really thought how to justify their answers. So they haven't really thought about reliability, fair tests, repeatability, and so forth. They've just done the experiment and got an answer. And it was only until the teacher said, well, who's the best one then? And that's quite important. Why? Justify your results, right then. In maintaining curiosity, I think we found 6 factors that did promote scientific achievement. I'll go through all 6 of these. You can read the document itself, and you'll find a section in the report that addresses each of those areas in terms of good practice. I just want to look at making science interesting, because that's the one that's connected to maintaining curiosity, and back again, practically based investigations. If you want, the science itself is interesting, not the teacher, but the science. But you need to get the science into their hands, into their experiences, through investigations. It's the scientific phenomenon itself that motivates. Then they start asking, why is it doing that? Raise their own questions. They're maintaining curiosity. So, again, as an inspector, this isn't rocket science. If we're inspecting a school, we'll do a work scrutiny and look at science and see if they've done any practical work in the sense of experiments, hopefully in an inquiry-based way. But we go to schools where once a term, something's got dirty. The rest of it is all bookwork. It's all correct, knowledge-wise, but there's been no experiment. There's been no attempt by a child to actually measure something or heat something or observe something. Well, that's really dull. Well, they don't want to do science post-16. They haven't actually done it pre-16, actually. They've just learned about it. I've sometimes used this analogy, which, no offence to football, by the way, but it's a bit like we've got a system in some schools where they'll teach the children the knowledge of football, like who won the FA Cup in 2005 or whatever it may be, who was the captain of England when that goal was scored. So they've got loads of facts, so they could do a kind of mastermind thing on football facts. They may even do, still, despite the changes proposed in some of the assessment systems, learn some skills. Keepy uppies and spot kicks and being able to head the ball. So they've got bunch of head knowledge, a bunch of physical skills because they've practiced it on the training pitch, but they haven't played the game. They've not joined that information together to actually play a football match. And science is joining the knowledge, prior knowledge and understanding, and your skills to actually do an investigation and find something out. And schools that think you can do it just by the knowledge and the skills stuff are not actually teaching science. Youngsters need to do some finding out for themselves. This what's it for question's critical. Oops. Go back up again there. Sometimes teachers might have to be provoked to do that. We'll ask children, what are you doing this for? When we're in a lesson, because I'm supposed to, is the usual answer. Or I'm trying to find out what the rule is about how light bounces off a mirror, which is a good answer. Give you another primary example about how a simple experiment can be made into an inquiry. Those of you that have physics in the secondary sector will know something called Newton's colour wheel. It's a disc with sectors of red, green and blue paint on it. Griffin and George, I think, make a little machine that's got a motor on the back of this thing. And so in a secondary school, Newton's colour wheel experiment is to gather around the desk and the teacher switches it on and this thing spins and the teacher then tells them that that sort of mucky yellow thing they're looking at really is white. And off they go and write that down that red, green and blue makes white. In a primary school, this is a first school, so we're talking year 4, 9-year-olds, I suppose. Same experiment, the teacher distributed to the entire class, and they were working in groups of 5 or 6, cardboard discs with 2 little holes in, marked out in sectors, and the children were said, okay, find out what combination of 3 colours, when you spin it, makes it white. And they were making these little spinners. You put a bit of string through these, you can make kind of spinners. Do you remember doing that at school? We used to put little razor blades, so you can make little circular saws out of them. Not razor blades, you know, segments. But anyway, you can make these spinners. It took them ages to get yellow, for want of a better phrase. And the teacher just let them try different combinations of colours. After a bit, the groups decided, rather than the entire group all making the same combination of colours, they should split and have different combinations, so it became 6 times more efficient, if you see what I mean, straight away. So already they are learning cooperative skills, team working, what have you. Fantastic. That's the same experiment, only done through an inquiry point of view. Of course, what's it for? Well, that's how TVs and colour photography works, etc., etc. There's no difficulty in linking the science ultimately into an application. That's the longer learning journey. That's where is it going? What am I doing this for? How does it connect with the bigger picture? We think this could be stereotypical, so please don't forgive me. I'm old now and will be stereotypical just because of how old I am. But we think girls at the sort of Key Stage 4 age are much more concerned about the what's it's for than boys, generally speaking. So the value, socially, if you like, or to making the world a better place, is more of an important agenda in your Key Stage 3-4 girls than it appears to be in Key Stage 4, and I'm generalising. All-girls school this was, again in the southwest, watching girls making little model transformers. You know how and they were doing the transformer equation, n1 over n2 equals r1 over whichever round it is. They were making model transformers, and yes, indeed, the needle on one side went there, and the other one went there, and so the thing was transforming stuff. What's it for? I asked the girls, what's this for? They had no idea. It's because it's in the syllabus. Could they answer the transformer question? Yes, they could. Did they know what transformers are for? No, they didn't. They've got pockets full of them, probably. They weren't supposed to have, of course, but they've got mobile phones all over the place. World is thick with transformers. But no application of what it was for, or even a fully understanding of the transmission grid, which is the bit that's usually used in the physics syllabus to how fantastic it is to raise the voltage up so you do. But even that isn't really understood by youngsters. They just remember the fact stuff. They don't even go to power stations these days. Have you noticed that? Trips to power stations. Anybody done a trip to a power station with their children recently? Did you go when you were being taught science? I bet some of you did do. They're fantastic, scary places that hum and they're really noisy and there's loads of energy going on. And that's missing. Most effective teachers constructed lessons that connected explicitly with other subject areas, particularly English and mathematics. They were not afraid to demand high literacy skills from children. Science teachers tend to dumb stuff down to get through stuff quicker. terms of the written work. That's a mistake. That's not going to improve children's literacy skills, by the way. Better to free respond than it is to fill gaps in a missing word passage. Sorry, everybody here. I've done it myself. Sometimes it's even mistakenly called by teachers closed procedures. You know, that kind of passage where a word's missing, down the bottom of the missing words, by the way, so that the kids can cross off the ones they put in. And once that goes wrong, of course, they're in real trouble. So if they put the wrong word in and crossed it up, they won't then think about putting the right word in later on. So they are mistakes. They won't improve understanding. They might improve recall, but they won't improve understanding. Better, give them a passage from New Scientist, miss out every 10th word, and see if they can reconstruct its meaning. Or if they're really able, miss out every 8th word, or whatever it might be, and then they'll have to reconstruct the meaning of the word that's missing and put the right word in. It might be "and" occasionally, or it might be a science keyword or whatever it might be. It doesn't matter, but they'll have to think, what does this passage mean? And that is valuable learning. And that actually probably is a closed procedure in terms of the technical term there. References to science in the media. This is old stuff now, but is anybody here that isn't with me? Do you remember that image? Baumgartner jumping out of a 130,000-foot balloon? Did you stop your teaching to share that, by the way? Did your lessons stop? And good, it should have happened, because that is science in the media. Quite why he did it. Somebody's gone higher now, by the way. Did you know that? Somebody's gone higher. They actually just went, did you see this? Baumgartner went up in this pressurised capsule thing, didn't he? And then jumped out of a great drama. It must be mad. Some other bloke's done it just on a kind of balloon attached to his harness and went up with the spacesuit itself. Not with any capsule, just with a balloon and then let go at 140,000 feet. But either way, science in the news. All the most recent stuff would be the Pluto flyby, for example, or Rosetta and the cometary landing. There's plenty of science about. Actually, I found a primary school in Cheshire that was doing, I got really good links with Ezra and the European Space Agency and Tim Peake's direct email somewhere or other. So they're emailing Tim and getting responses back from him directly. And these kids were modelling and had got some seeds to go into space on a space lab. Yeah, come across this one? And there they all were watching this thing being launched from French Guiana, and it went wrong. Do you remember that? It's not that long ago. And there's this enormous explosion. Nobody was hurt in the explosion. The teacher had to make this clear before she showed the video. There wasn't anybody on the rocket, don't worry. But these kids were going, and okay, it went right occasionally, but they were really engaged in contemporary science. And those particular lot were also watching videos of that. There's an Italian astronaut that's come back from being the longest serving woman in space. I can't remember her name now. There was live re-entry footage of the Soyuz thing landing. Well, land's the wrong phrase. It sort of crashes with the ground, doesn't it, ultimately? It's a pretty hard thump that it makes. And of the hatch being opened and this poor lady being dragged out, literally limped off, having been in space 200 days, she could not hold her hand up. And for the first time, these youngsters of the glamour of space suddenly realised, gosh, is she dead? She wasn't. She booked up after a couple of hours type of thing, but anyway, real live science. Fascinating. Try their own interest. And there's another one, stump the teacher. There's all sorts of ways of doing this. Be careful, but there's a school that asks kids to bring their own questions in, which the teacher then edited before putting them on a public display board. But kids will, once you get used to that, they'll be really honest and very quickly get to the edge of everybody's science understanding, and the teacher will say, actually, I don't know myself. Let's see if we can find out. Or, that's a good question, we haven't got a clue. Now, I'm not going to take a lot of time, but you'd be interested to know that our Secretary of State thinks that working scientifically, which is the scientific inquiry-based learning that's in the national curriculum, no problem about defining what it is, should be embedded in the subject context across all 3 science disciplines. So it's not that Ofsted doesn't know, the government doesn't know, education researchers don't know. What else do we need to do to share with you how important scientific inquiry is? It is what science teaching actually is. And if you've got leaders in your school that don't let you do it because of time or resource complaints, show them that. Show them Ofsted's maintaining curiosity. And, by the way, these subject leaders should include sufficient weekly curriculum time, sufficient laboratory space to make sure kids have the time to do scientific inquiry properly. And when Ofsted makes these recommendations, we don't do it lightly. Our lawyers crawl over all this stuff before we publish it. So if a school isn't doing it, then we can say, well, you're not actually following our recommendations. Call yourself a good school? Why aren't you following the recommendations? There may be a good reason, of course, possibly. Difficult to think of one, but they might come up with an explanation that lets them off. But there's no wriggle room, there's no hiding from the legislative system and the inspection system that this is what we're expecting to find. And we're expecting schools to provide you with professional development, not just in science, of course, but for science teachers. Why aren't you doing it? Don't you want your science teachers to be better then? It's just slightly harshly here. Subject leaders need to make sure that they know what's going on, especially in primary schools. And in secondary schools, what are different groups of children doing is, for instance, if you look at your split in groups between single award, dual award or triple science or whatever, is there a difference in the proportions of disadvantaged kids in each of those strands? And if the answer is yes, there is, then you're damaging equity in your school. So if you've got more disadvantaged children doing one particular track than another, why? What is it about disadvantaged children, and I'm jumping to a conclusion here, why are they all mainly doing core science and your less disadvantaged ones are doing triple? That's not right, that's not fair, that's not equitous. So make sure you're analysing that before you're claiming that the school's inclusive. It could be because of some daft connection to their prior attainment at Key Stage 2's locked low attaining pupils into a core science route, but that's not right. Don't believe low incoming data, by the way. It doesn't mean that ascension was right. It just could be that being taught properly at primary schools. Develop literacy. This is a recommendation. Use science as a motivating context for students. And we've said this already, it's not rocket science, but very quickly, I'm just going to nip through. 4 minutes, is that about right? You can quiz me later at the panel meeting if you disagree with all of this, but my inspectors, bless them, will be looking for this. We'll be checking how well teachers understand the big ideas of science. This is subject knowledge stuff. We'll be checking how well pupils master investigative and practical skills. That means they've got to do investigations in practical skills before they can get anywhere near mastering it. How do pupils find out for themselves? Do teachers monitor how well children are doing, particularly by different groups, reasons they're making choices, girls and boys, progression post-16 and what have you? And how much time do you provide them? I'm not going to say you must spend 4 hours, 32 minutes and 10 seconds a week or whatever silly like that. But we will say, if you're doing triple science, then by and large it should have more or less the same time as any other 3 subjects that GCSE should have. And if you're trying to squeeze triple science into the space of 2, you are making a mistake because you'll squash the practical time doing that, and you'll end up with kids getting the grades and not doing science. And that's why they drop off post-16, because they haven't done the science. They've got the grades, but they haven't done the science. They don't like it. They don't want to carry on with that experience, thank you very much. So be careful. Triple science should be for those youngsters that want to do more science, spend more time doing science, not to try and squeeze 3 out for the price of 2. Check pupils have got a say in what they're doing. Don't follow recipes and what have you, but they're constructing investigations, at least in part, by themselves. Make sure pupils know how to improve their science understanding, so give them feedback that stretches them, challenges them, congratulates them, and agrees that nobody knows the answer to that question occasionally as well. And then link literacy with science and interesting. That's easy to do, but if you're not sure about how to do this, talk to your English faculty. They'll love it if you say, okay, we'll use all our science homework time this term to improve their literacy. We'll ask them to do stuff, but help us with the literacy you're trying to develop, whatever it might be, writing skills, but we'll use science content or context to help youngsters find that motivating, like find out why Fitzharbour's second wife left him, for example. make sure you track what they're doing, and so you can sort of intervene if necessary, if they're falling behind, or even if they're accelerating. Actually, gosh, they're going really quickly. I don't need to go through this all again with this lot. They can skip to the next stage. And make sure you've got access, or make your leaders make sure you've got access to specific science development. I rest my case. Thank you very much.